Welcome to rfhammer.com. This video gives an overview of the RF Amplifier Design and Simulation software from rfhammer.com. Download the software from the website rfhammer.com, save the exe icon and FET-S parameter files to your PC, all in the same directory. It could take a while to unbundle the first time you run it, but it should run on all standard Windows 10 machines. The first window you'll see when you run will be the following. So here's the window. The first window you'll see. You can select between lumped element and transmission line topologies for the matching networks of the amplifier. And you see over here we have the selection for lumped element L section high pass matching network. You can also go to a transmission line where the matching networks will then be series transmission line and open circuit stubs. Right, let's go back to a lump element and select that, and we see the next window which opens. So RF amplifier L section high pass. There are 4 windows which you can see. The first one being the circuit parameters. Then we have the transistor or the FET field effect transistor S parameter S2P file format with the name of the file. We have the plot parameters, and then the plot selection, so we can select between the stability factor mu, stability circles, and the amplifier response S11, S21 and S22. Okay, so let's have a look at these windows in a bit more detail. So we have the circuit parameters, we have the amplitude, the amplifier frequency, center frequency, design frequency. So the amplifier will be designed at this center frequency. The inductor Q, if you want an ideal circuit, just make this value very large. Z0 is always 50 ohms. We can also have impedance of, not impedance, we can have stabilizing resistor circuit, which we can use to improve the stability. Over here we have the S parameter file format. So over here we have the name. So obviously the name of your file must be the same as what we input here. So it'll be the S2P file, which you would then input here. The frequency you must designate. Over here, this file uses gigahertz for the frequency. It uses numeric or magnitude for the magnitude of the S parameters, and then also in degrees and not in radians. So over here we have the stability factors. We can plot the stability factor, the start and the stop frequencies, the number of frequencies, the marker we can stipulate, stability circles, where frequency we start at and the frequency we stop at, the number of stability circles we want to plot in this frequency range, and then the amplifier frequency response, the start, stop frequency, and a marker. Okay, let's run this. Okay, so there you can see the output for this these values which we've inputted. Okay, so here we're seeing the stability factor mu between these frequencies. Obviously the the start and stop frequency must be within your limits of your S parameter file. Then we can also plot the stability circles. Okay, so there we have 3 stability circles. The starting circle, which starts at 2 gigahertz, is the dotted lines. We can make a number of circles, 20 circles, whatever you want, between these two limits. And then let's just run that again. We can then also have the amplifier frequency response. So there we see the amplitude, the gain in the blue curve, and the matching input and the output match in the orange and green curve. Okay, so let's have a look at the circuit. So here we see the design circuit. In this case, we have selected, we have no stabilizing resistors, a series resistor, input R1, and the parallel one R2. This is 0, so there's no resistance. This is a very high value for the parallel resistor, so it's also not there, and similarly for the output. Then we see the designed parameters for the matching circuit, so it's a high pass lumped element. So the inductor L2 has a value of 0.47 nanohenry. C1, yes, C1, so it's 1.3 picofarads. And similarly then for C3, 0.714 picofarads, and the inductor L4 is 1.039 nanohenry. And the resistor values are basically 0 and a very high value for the parallel stabilizing resistor. Okay, so let's have a look now. Okay, let's just go back to the S parameters. Let's just open the S parameter file here. Okay, so here we have the S parameter file. So this is a mini circuits FET, field effect transistor. Data is provided by monolithics. But if we actually go then to the format, we can see 3 gigahertz. So the frequency here is in gigahertz. The S parameter magnitude is in magnitude, so I call it numeric. And we can see then the degrees. So this is the frequency, this is S11. So this is the degrees of S11, and we can see that it's in degrees and not in radians. And it starts at 0.1 gigahertz and goes all the way up to I think it's 18 gigahertz. Let's just move down. Okay, so it goes to 18 gigahertz. And we see there's no noise parameters here. So obviously now when we stipulate the start and stop frequencies for the stability factor, we can't go above 18 gigahertz and we can't go below 0.1 gigahertz. Okay, now the important thing is, so we must have select the correct format, and all the comment lines must be commented out either with a exclamation mark or a hash. Otherwise you'll get an error when you read the file, and quite often some files have a noise parameters down here, so then you must either just comment those out or delete them. Okay, but make sure your S parameter file has the right format, otherwise they won't run correctly. Okay, let's close that. Okay, let's go back to the stability factor. Okay, so here we have the stability factor. And we can see that obviously the mu factor must be above 1. So we see we have a stability range here of around about 0.4 gigahertz to just above 10 gigahertz. And we're designing at 4 gigahertz, so mu is greater than 1, but it's a bit marginal. So we can now increase the stability range, the stability bandwidth, by using these stabilization resistors. So you can either have a series resistor at the input or output, or a parallel at the input or output, or you can have all 4. But let's start now. We can have a look at the stability circles. So mu is basically the distance from the center of the Smith chart to the tangential line to the stability circle. And it's quite nice because there's only one factor we have to worry about, mu. And the larger mu is, the more stable the device is going to be. So that's quite nice. And obviously we can see now that at 2 gigahertz we have stability circles indicating that the device is unstable. They're within the Smith chart, and that also corresponds then to the plot of mu. Okay, so let's make this. We can play around now with the stability circles. Let's make that 10 and see what happens. Obviously the stability circles will have an influence now on the output, on the gain and the compression point. But we see this increased stability is increased down to nearly 2 gigahertz from 4. So that's nice. And we can run that again. The stability circles. Okay, they've moved out. They're still just within the Smith chart for 2 gigahertz start. The amplitude, as we can expect, the gain has decreased slightly. And so we can play around now with these stabilization resistors. Let's put a 400 ohm parallel resistor on the output. So what does that do? Okay, has increased it down to 2 gigahertz. Starts at 2 gigahertz. Instability below 2 gigahertz will start. And then the output, we nearly gain around up to 14, 16 gigahertz. So let's have a look at the stability circles. Okay, so we can see they're basically out the Smith chart. Very within, if we look over here, perhaps just within the 2 gigahertz. Okay, let's put a 5 gigahertz in the input. Okay, there we definitely stable at 2 gigahertz. So let's have a look at the stability circles. Yeah, so that's fine. We can look at the response. Okay, obviously the gain has reduced again, and if you have a resistor on the input, it's going to affect your noise figure as well. So quite often you don't really want to do that. But yeah, so there we have the stability factor mu. We have the stability circles, and then we have the amplitude. Or we have the frequency response, gain, and the reflection coefficients. And once again, now we have the values of the stabilizing resistors, which we can then use. Okay, so we can also then use other different experimenter file. I've got one here on my clipboard, so we can then just replace it with this one. Okay, so yeah, now we have an Infineon transistor, BFR92, and once again, if you look at the S parameter file, it's also in gigahertz. The magnitude is numeric and the angles in degrees, so we don't have to worry about that. But the S parameter file only goes up to 6 gigahertz. I'm going to change this to 6 gigahertz. Okay, 6 gigahertz. And let's have a look what that looks like. Okay. Okay, so there we have the mu stability factor. Okay, so we can see it's stable to quite a low frequency. So this is perhaps a nicer low frequency transistor to use. And then stable right up to 6 gigahertz. So we can do a design at 4 gigahertz. Let's run that. 4 gigahertz. Okay, hasn't got much gain at that frequency, so there's not much use. So let's go down to a lower frequency. So let's go down to 1 gigahertz. Let's do design at 1 gigahertz. And then the stability circles can start at 1 gigahertz. Well, that's still going to be, we're still within the stable region, so they're all going to be outside the Smith chart. And let's then have our marker also at 1 gigahertz. Over here we can also have a marker at 1 gigahertz, and we can run that. Okay, Okay, what's it saying here? F0 multiplication and F start. Okay, so we just have to have a look at the frequency ranges here. Okay, we're starting over here at 1 gigahertz. Okay, so obviously this can't be at 2 gigahertz. So let's make this down then. Let's make this to 500 megs. Okay, let's run that. Okay, so at 1 gigahertz, we see we have a gain of 11, 17. Okay, so that's okay, but let's just go back to the stability factor. Okay, and let's see what happens now if we remove these stabilizing resistors. Okay, that's still looking okay. Okay, what's happening now? Okay, that's made a bit of a difference, but it's still stable. If we make this 0, okay, it's still stable, although at the high frequency end it is a bit low. So let's leave that at 10 for a matter of interest. Stable into a much higher frequency. Can run that. Okay, so there we also have another amplifier, gains a bit higher. Stability, you see, yeah, no, this is quite I don't know, 500 megs perhaps. So for the stability circles, it's going to be fine. Over here, let's make this 500. Yeah, so we're a bit marginal here in terms of the output stability. But anyway, so we have a amplifier here. So we have the amplifier values, we have the stabilization factor values, and there's our amplifier. Okay, so that was the lumped element. Let's go to the transmission line. This is basically the same. Well, everything's the same except now that we have a transmission line matching network. Okay, we're back to the mini circuits transistor here, and you can run the amplifier. These two are going to be the same. It's just the amplifier is going to be different because we're using transmission lines now. So there we see the value of the transmission lines. We see that the Z0 is always 50 ohms, so that's 50 ohms. Here we have the electrical length of the transmission lines. So Z1, so there we have Z1, which is an open circuit stub, no short. That's why we're using open circuits. And then we have the series transmission line, electrical length, and then Z3 is the output open circuit stub, each electrical length, and then also the series transmission line on the output. Okay, so this is basically, the rest works are basically the same. We just then have a transmission line matching network. Right, thank you for watching this video. Remember to visit rfhammer.com. There are many more design and simulation software programs there. Thank you.